Okay, so I wanted to talk about the combined gas law. And what that is when you have one gas and that gas is described under two different environments. Oops. So let's say you have a gas and in one situation and something changes, the temperature changes or the pressure changes, or both the temperature and the pressure change. But you have these two different environments that happen. So your book goes through this like flow chart of how to do these problems and what to do. But I want to teach you guys a trick to this. And the trick is you have PV equals nRT. And this ideal gas law is used in one environment. So I take and I put 1 next to all the numbers. Okay, so that 1 is one environment. And then I say, okay, the gas is going to change and go into a different environment. So when it goes into a different environment, I'm going to use the same PV equals nRT, only this time I'm going to put 2's. So now I have this combined gas law where I'm talking about one gas, so let's say helium, and I'm going to describe it under two different environments. Now, I have this whole thing, and what I need to do to simplify this is cancel out what stays the same. So in your book, it has a combined gas law that you have to memorize, but this is a shortcut. You just need to memorize PV equals nRT, and you have that memorized already. And because you're using two different environments, you're going to use it twice. Okay, when I cancel what stays the same, then R, for example, that's a constant on the top divided by the constant on the bottom, will cancel out. Okay, so we're going to go through an example of this. And the cool thing about this combined gas law, and especially doing it this way, is you don't need to memorize individual gas laws. So if you ever have a problem or a question where it gives you one gas, two different environments, you can use this setup every single time and simplify it by canceling out what stays the same. Okay, so I want to go through an example of this. And so this example says a 22-liter cylinder of helium. So in this cylinder right here is helium gas, has a pressure of 150 atm. This is huge. This is a huge pressure at 31 degrees Celsius. Okay, so we have helium that's in a cylinder. Okay, well, we're going to have a party. And the day of the party, the atmospheric pressure, so the pressure around us, is 755 millimeters of mercury. And the temperature is colder. The temperature is 22 degrees Celsius, which is about room temperature. So it's cooled off a little bit. It's a perfect day for a party. And so we want to know how many liter balloons can be filled. Okay, so to do this, we have to take the helium from the cylinder and take it out of the cylinder. So 1 is helium in the cylinder and 2 is helium out of the cylinder. And when we take it out of the cylinder, we need to put it into balloons. Okay, so what I do with this is I kind of make two tables. Okay, so I'm going to go to the next slide. It has the question up here. And I have helium in my cylinder. And I have helium out of the cylinder. Okay, and so then I go through and look. So a 22-liter cylinder. So the volume of the helium in the cylinder is 22 liters. Okay, that has a pressure And I'm saying, okay, I'm going to call all of these one. It has a pressure of 150 atm. Okay, and the temperature is 31 degrees Celsius. And I'm automatically going to just convert that to 304 Kelvin. Okay, so helium in the cylinder is situation 1, and I've written up 1, 1, 1. Now I'm going to take the helium out of the cylinder. Okay, and out of the cylinder at the party, we want to know how many liters of helium are out of that cylinder. Okay, I know the atmospheric pressure is 755 millimeters of mercury. And I'm going to convert that right away. 760 millimeters of mercury equals 1 atm. So this equals 0.993 atm. Okay, so my situation 2, I want to know that volume. I have pressure of 2, and the temperature of 2 is 22 degrees Celsius. I'm going to convert that right away to Kelvin. And that's 295 Kelvin. Okay, so now I have volume, pressure, temperature, volume, pressure, temperature. Okay, now remember I take P1, V1 equals N1, R1, T1 divided by P2, V2 equals N2, R2, T2. Okay, so I have volume, I have pressure, I have temperature. I have pressure, maybe I'll do a different color. I have pressure, I have volume, I have temperature, right? I've got these 3. Over here, I want to find volume. I have pressure, and I have temperature. Okay, so now looking at this equation, well, the amount of helium is going to be the same whether it's in the cylinder or out of the cylinder, right? So N is going to be exactly the same. So N1 equals N2, and I can cancel those out of my equation. Okay, R is a constant. That R is going to be the same in situation 1 and situation 2. So those get canceled out of my equation. Okay, so I'm left with a simplified equation where I want to solve for V2. I'm going to go to the next slide. All of this information should still be there. So I have my helium in the cylinder, and I have my helium in the balloons. Okay, I have V1, P1, T1, V2 liters of helium. I say in the balloons, but also that's out of the cylinder. Okay, so I'm going to write this up. P1 V1 over P2 V2 equals T1 over T2. Because N and R are the same in both cases, I've taken them out of my equation. Okay, my goal is to find V2. So I want to find this one right here. Okay, so to do that, I'm going to multiply both sides by V2. That cancels here. Next, I'm going to take and divide by this, or multiply by T2 and divide by T1. But either way, it comes over here and it flips itself upside down. So T2 over T1, P1, P2 equals V2, right? So this is so much easier to manipulate these variables and then put the numbers in. So V2 equals T2. Oh, I forgot V1. P1 V1 divided by T1 divided by P2. Okay, so far so good. Okay, so I'm going to go to the next slide where I've taken and I have this all rearranged. So volume 2 is what I'm looking for, okay? And that's the helium out of the cylinder. And I put that helium out of the cylinder and I put it into balloons, okay? Okay, so I had a question about how do I rearrange this? So I'm going to back up and just go through that one more time so you guys can see. So I need to get V2 by itself. Maybe I'll just write this up here again like this and just do it twice for you guys. Okay, so I need to get V2 by itself. And when I do that, I generally want it to be on the top, right? So because it's on the bottom here, I'm going to multiply both sides by V2. When I multiply something that's on the bottom, it cancels. And I'm left with P1 V1 over P2 equals T1 over T2 times V2. Okay. Next, I need to get this on this side. So if I multiply both sides by T2, it divides there, and I put T2 on the top. Okay. Now I have T1 V2. So what I'm going to do next is divide by T1. And I'm going to divide both sides by T1. And when I do that, the T1 cancels with the T1 here. Okay, so everything on this side is canceled except for the V2. And you get V2 equals T2 times P1 V1 over T1 P2. Does that make sense? I found it's easier to rearrange these first rather than put all the numbers in and then rearrange them. Okay, you guys ask me questions like that all the time because you're not the only one that has those types of questions. Okay, so next what we have to do is be really, really careful, right? We have V2 here. So our helium in the cylinders are the ones and our heliums out of the cylinders are the twos. You have to pay really, really close attention. So I'm going to take and put these variables, I guess, into my equation. So P1 here is 150 ATM, okay? And that's helium that's in the cylinder. V1 is also in the cylinder. So I'm going to come up here and put 22 liters. That 22 liters is in the cylinder. Oh my gosh, sorry guys. Next, I have T2. And that T2 is out of the cylinder. So let's change colors and find the T2 out of the cylinder. Oh, thank you guys. I feel bad for everyone wearing headphones that I just sneezed in their headphones. Okay, so T2 is out of the cylinder. I'm going to divide that by P2, which is out of the cylinder. And then divide that by T1, which is 304. So this is in, and this is out. Okay, so I have these situations, two different things. So now I want to find V2 that's out of the cylinder. Okay, when you do this in your calculator, the easiest thing is you take 150 times 22 times 295 divided by 0.993 divided by 304. Okay, so that's how you enter it. Or you can multiply the top numbers together and multiply the bottom numbers together and then divide. Okay, so make sure you're using those orders of operation. So multiply, 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 divide, divide. When you do this, let me get my yellow or my orange. ATM cancels with ATM, Kelvin cancels with Kelvin, and look, you're left with liters. So the number I get is 3,224.8 liters. Okay. And I went through and I looked, there's 3 significant figures. There's 2 significant figures, 3, 3, 3. And so my answer has 2 significant figures, right? So I have 2 tall numbers, and then I write the rest of them small to just keep track of those significant figures. Okay, so this is the volume out of the cylinder, right? So let's go back and read our question. And the question says, how many 5-liter balloons can be filled? What that tells me is 1 balloon equals 5 liters of helium, right? So if I take my helium in the cylinder, I take it out of the cylinder, I need 5 liters of helium to fill every balloon, right? So I have found my liters of helium out of the cylinder. So next I need to convert that to balloons, okay? So I know that for 5 liters of helium out of the cylinder, that will fill 1 balloon. Okay, so liters of helium cancels with liters of helium. I take this number and divide by 5, and I get 640 balloons. Okay, now I only have 2 significant figures, which means I have 64 or 640 here, right? And if I can only have 2 significant figures, then I need to take and simplify that number. So I can fill 640 balloons.